Chapter 7, Higher Order Functions. In this chapter we introduce higher order functions, which allow common programming patterns to be encapsulated as functions. We start by explaining what higher order functions are and why they are useful, then introduce a number of higher order functions from the standard prelude, and conclude by implementing a binary string transmitter and two voting algorithms. 7.1 Basic Concepts. As we have seen in previous chapters, functions with multiple arguments are usually defined in Haskell using the notion of currying. That is, the arguments are taken one at a time by exploding the fact that functions can return functions as results. For example, the definition add int, add xy is x plus y, means add blah blah blah, and states that add is a function that takes an integer x and returns a function, which in turn takes another integer y and returns their sum, x plus y. In Haskell, it is also permissible to define functions that take functions as arguments. For example, a function that takes a function and a value and returns the result of applying the function twice to the value can be defined as follows. Twice is a function that takes a function from a to a, takes an a, and returns an a. Twice f of x is f of x. For example, twice 2 times of 3 is 12. Twice reverse of 1, 2, 3 is 1, 2, 3. Moreover, because twice is a curried function, it can be partially applied with just one argument to build other useful functions. For example, a function that quadruples a number is given by twice times 2. And the fact that reversing a finite list twice has no effect. I, captured by the equation twice reverse, is id, where id is the identity function defined by id x is x. Formally speaking, a function that takes a function as an argument or returns a function as a result is called a higher order function. In practice, however, because the term curried already exists for returning functions as results, the term higher order is often just used for taking functions as arguments. It is this latter interpretation that is the subject of this chapter. Using higher order functions considerably increases the power of Haskell by allowing common programming patterns to be encapsulated as functions within the language itself. More generally, higher order functions can be used to define domain-specific languages within Haskell. For example, in this chapter we present a simple language for processing lists, and in part 2 of the book we will develop languages for a range of other domains, including interactive programming, effectful programming, and building parsers. 7.2 Processing Lists. The standard prelude defines a number of useful higher order functions for processing lists. Many of these are actually generic functions that can be used with a wide range of different types, but here we restrict our attention to lists. As our first example, the function map applies a function to all elements of a list and can be defined using a list comprehension as follows. That is, map f of x's returns the list of all values f of x such that x is an element of the argument list x's. For example, we have map plus 1 over 1, 3, 5, 7 is 2, 4, 6, 8. Map even of 1, 2, 3, 4 is false, true, false, true. Map reverse, we get the point. There are 3 further points to note about map. First of all, it is a polymorphic function that can be applied to lists of any type, as are most higher order functions on lists. Secondly, it can be applied to itself to process nested lists. For example, the function map plus 1 increments each number in a list of lists of numbers, as shown in the following calculation. Oh, that's pretty cool. And finally, the function map can also be defined using recursion. That is, applying a function to all elements of the list gives the empty list, while for a non-empty list, the function is simply applied to the head of the list and we then proceed to apply the function to all elements of the tail. The original definition for a map using a list comprehension is simpler, but the recursive definition is preferable for reasoning purposes. See chapter 16. Another useful higher order library function is filter, which selects all elements of a list that satisfy a predicate, where a predicate or property is a function that returns a logical value. As with map, the function filter also has a simple definition using a list comprehension. Filter takes a function from A to bool, a list of A's, and returns a list of A's. Filter P of X's is defined as X such that X taken from X's and P of X. That is, filter P X's returns the list of all values X such that X is an element of the list X's and the value of Px is true. For example, filter even from the list 1 to 10 is 2, 4, 6, 8, 10. Filter greater than 5 on the list 1 to 10 is 6, 7, 8, 9, 10. Okay, as with map, the function filter can be applied to lists of any type and can be defined using recursion for the purposes of reasoning. For the purposes of reasoning, I don't really understand why he's saying that. Filter P of the empty list is the empty list. Filter P of X's is P of X. If P of X, then X cons filter P of X. Filter P X's, otherwise is filter P X's. That is, selecting all elements that satisfy a predicate from the empty list gives the empty list, while for a non-empty list, the result depends upon whether the head satisfies the predicate. If it does, then the head is retained, and then we proceed to filter elements from the tail of the list. Otherwise, the head is discarded, and we simply filter elements from the tail. The functions map and filter are often used together in programs, with filter being used to select certain elements from the list, each of which is then transformed using map. For example, a function that returns the sum of the squares of the even integers from a list could be defined as follows. Sum square even. List of ints to int. Sum square even. Sum map to the power of 2 filter even ends. We conclude this section by illustrating a number of other higher order functions for processing lists that are defined in the standard prelude. Decide if all elements of a list satisfy a predicate. All, even 2, 4, 6, 8. Decide if any element of a list satisfies a predicate. Any, odd, 2, 4, 6, 8, false. Select elements from a list while they satisfy a predicate. Take while, even. Remove elements from a list while they satisfy a predicate. Drop while, odd. The fold R function. Many functions that take lists as their argument can be defined using the following simple pattern of recursion on lists. That is, the function maps the empty list to a value v and any non-empty list to an operator hashtag, applied to the head of a list and the result of recursively processing the tail. For example, a number of familiar library functions on lists can be defined using this pattern of recursion. Sum of the empty list is 0, sum of x and x's is x plus sum of x's. Yatta yatta yatta. The higher order library function fold R, abbreviating fold right, encapsulates this pattern of recursion for defining functions on lists, with the operator hashtag and the value v as arguments. For example, using fold R, the 4 definitions above can be rewritten more compactly as follows. Recall that operators must be parenthesized when used as arguments. These new definitions could also include explicit list arguments, as in some x's. Okay. But we prefer the above definitions in which these arguments are made implicit using partial application because they are simpler. Debatable. The fold-OR function itself can be defined using recursion. That is, the function fold-R fv maps the empty list to the value v and any non-empty list to the function f applied to the head of the list and the recursively processed tail. In practice, however, it is best to think of the behavior of fold-R fv in a non-recursive manner, as simply replacing each cons operator in the list by the function f and the empty list at the end by the value v. For example, applying the function fold-R plus 0 to the list gives the result, in which the cons and empty list have been replaced by plus and 0 respectively. Hence, the definition sum equals fold-R plus 0 states that summing a list of numbers amounts to replacing each cons by addition and the empty list by 0. Even though fold-R encapsulates a simple pattern of recursion, it can be used to define many more functions that might first be expected. First of all, recall the following definition for the library function length. For example, applying length to the list 1, 2, 3 gives the result 1 plus 1 plus 1 plus 0. That is, calculating the length of a list amounts to replacing each cons by the function that adds 1 to its second argument, and the empty list by 0. Hence, the definition for length can be rewritten using fold-R. Now, let us consider... So this is a lambda that takes 2 arguments. Yeah, okay, so this is the element of the list, and this is the thing that accumulates. Okay. Now let us consider the library function that reverses a list, which can be defined in a simple manner using explicit recursion as follows. For example, applying reverse to a list 1, 2, 3, 4 gives the result empty list plus 3, blah, blah, blah. It is perhaps not clear from the definition of the example how reverse can be defined using fold-R. However, if we define a function snock, x x's is x's plus plus the list that contains x, that adds a new element at the end of the list rather than at the start. Snock is cons backwards. What the fuck? Then reverse can be defined as reverse empty list is empty list, reverse x x's is snock x, reverse x's. From which a definition using fold-R is then immediate. Reverse is fold-R snock empty list. That's very cool. We conclude this section by noting that the name fold-right reflects the use of an operator that is assumed to associate to the right. For example, evaluating fold-R plus 0, 1, 2, 3 gives the result 1 plus 2 plus 3 plus 0, in which the bracketing specifies that addition is assumed to associate to the right. More generally, the behavior of fold-R can be summarized as follows. The fold-L function. It is also possible to define recursive functions on lists using an operator that is assumed to associate to the left. For example, this function sum can be redefined in this manner by using an auxiliary function sum prime that takes an extra argument v that is used to accumulate the final result. For example, sum 1, 2, 3, applying sum 0, 1, 2, 3. Sum prime 0 plus 1, 2, 3. The bracketing in this calculation specifies that addition is now assumed to associate to the left. In practice, however, the order of association does not affect the value of the result in this case, because addition is associative. That is, x plus y plus z is the same as x plus y plus z for any numbers x and y, x, y, and z. Generalizing from the sum example, many functions on lists can be defined using the following simple pattern of recursion. Fv of the empty list is v, fvx, x's is fv hashtag xx's. That is, the function maps the empty list to the accumulator value v, and any non-empty list to the result of recursively processing the tail using a new accumulator value obtained by applying an operator hashtag to the current value in the head of the list. The higher order library function fold_L, abbreviating fold left, encapsulates this pattern of recursion with the operator hashtag and the accumulator v as arguments. For example, using fold_L, the above definition for the function sum can be written more compactly as follows. Similarly, we have the other fold_R examples from the previous section can also be redefined using fold_L by supplying the appropriate operators. For example, with these new definitions, isn't this just the same? I mean, I understand that it's now like putting the accumulator to the left and then applying everything to the right. But okay. When a function can be defined using both fold_R and fold_L as in the above examples, the choice of which definition is preferable is usually made on grounds of efficiency and requires careful considerations of the evaluation mechanism underlying Haskell, which is discussed in chapter 15. The fold_L function itself can be defined using recursion. In practice, however, as with fold_R, it is best to think of the behavior of fold_L in a non-recursive manner in terms of an operator hashtag that is assumed to associate to the left, as is summarized by the following equation. The composition operator. The higher order library operator dot returns the composition of two functions as a single function and can be defined as follows. So dot is a function that takes two functions, one from B to C and one from A to B, and returns a function from A to C. It's odd. Why wouldn't they reverse these two arguments? That seems a lot more logical to me. Oh no, because it's like the after thing from mathematics. F after G. That is, f dot g, which is read as f composed with g, is the function that takes an argument x, applies the function g to its argument, and applies the function f to the result. This operator could also be defined by f composed with g of x is f of g of x. However, we prefer the above definition in which the x argument is shunted to the body of the definition using a lambda expression, because it makes explicit the idea that composition returns a function as its result. Composition can be used to simplify nested function applications by reducing parentheses and avoiding the need to explicitly refer to the initial argument. For example, using composition, the definitions odd n is not even n. Odd n is not even n. Twice f of x is f of x. Okay, and then he's rewriting them below. Okay, so odd and not even n can be defined as not composed with even. Oh yeah, that is quite elegant. I swear there is also an operator in Haskell that I thought it was just an exclamation mark, but I tried it earlier and it didn't work. That first evaluates everything that comes after it, and that way you can also reduce the amount of parentheses you need to write. Maybe it's the pipe. Wait, let's try that. I need to position my microphone somewhere. Because I need both my hands to type. Yes. For example, let's say we define a function f equal to and g equal to +1. Now if we do f of g of 1, we get that, but we can also do no. Oh, no, it's doing that again. Oh. So that works, but I really thought... No. It's dollar. Oh. Okay. Yep. Yeah. Composition also has an identity given by the identity function. That is, id is the function that simply returns its argument unchanged and has the property that if that id composed with f is f and f composed with id is f for any function f, the identity function is often useful when reasoning about programs and also provides a suitable starting point for a sequence of compositions. For example, the composition of a list of functions can be defined as follows. Interesting. This, I feel like Haskell is very abstract algebra. Like it has people that made it are mathematical. 7.6 Binary String Transmitter. We conclude this chapter with two extended programming examples. First of all, we consider the problem of simulating the transmission of a string of characters in low-level form as a list of binary digits. Binary numbers. As a consequence of having 10 fingers, people normally find it most convenient to use numbers written in base 10 or decimal notation. A decimal number is sequence of digits in the range 0 to 9, in which the rightmost digit has a weight of 1, and successive digits as we move to the left in the number increase its weight by a factor of 10. For example, yes, we understand decimal notation, dude. In contrast, computers normally find it more convenient to use numbers written in the more primitive base 2 or binary notation. A binary number is a sequence of zeros and ones called binary digits or bits, in which successive bits as we move to the left increase in weight by a factor of 2. For example, the binary number 1101 can be understood as follows. Yes, we know. Base conversion. We begin by importing the library of useful functions on characters. We already have that for some reason. To make the types of the functions that we define more meaningful, we declare a type for bits as a synonym for the type of integers. Type bit is int. A binary number represented as a list of bits can be converted into an integer by simply evaluating the appropriate weighted sum. A binary number represented as a list of bits can be converted into an integer by simply evaluating the appropriate weighted sum? What? Okay, yeah. Binary to integer. So weights, what is it, iterate again? Has he already explained that? Oh no. Huh? So oh no, my computer is lagging now. I think it filled up some okay. So I'm pretty sure he hasn't explained iterate before. So he's explaining it here. The higher order library function iterate produces an infinite list by applying a function an increasing number of times to a value. Hence, the expression iterate times to 1 is in the definition of binary to int produces a list of weights, which is then used to compute the weighted sum by means of a list comprehension. Wow, that's very clever. Wait, I'm gonna restart Emacs. Okay. Bin to int. Where weights is iterate. No, I wrote it wrong. Oh. The higher order library function iterate. Oh yeah, we just read that. There is, however, a simpler way to define bin to int, which can be revealed with the aid of some algebra. Consider an arbitrary 4-bit binary number, ABCD. Applying bin to int to this list will produce the weighted sum, which can be reconstructed as follows. Simplifying 1 times a, factoring out 2, factoring out 2 times, complicating D. The final result shows that converting a list of bits ABCD into an integer amounts to replacing each cons by the function that adds its first argument to twice its second argument and replacing the empty list by 0. More generally, we conclude that bin to int can be rewritten using fold R. Okay, I don't really get it. So the function is times plus 2 times, and then this is 0 plus 2 times. That's very cool. It's doing it in reverse though. Right? Because that would be, I don't know, but it would be a different number. If I do 1, 0, this is supposed to be 2, right? But it's a 1. Why did he make it so weird? I mean, why is it back to front? The final result shows that converting a list of bits ABCD, or should I have used, no, fold R. Now let us consider the opposite conversion from a non-negative integer into a binary number. This can be achieved by repeatedly dividing the integer by 2 and taking the remainder until the integer becomes 0. For example, starting with the integer 13, we proceed as follows. 13 divided by 2 is 6, remainder 1. The sequence of remainders 1011 provides the binary representation of the integer 13. It is easy to implement this procedure using recursion. We will ensure that all our binary numbers have the same length, in this case 8 bits, by using a function make8 that truncates or extends a binary number as appropriate to make it precisely 8 bits. Make8. Okay. Wait, I didn't really take 8 bits plus repeat 0. And repeat is just an infinite list, right? Produces an infinite list of copies of a value, but lazy evaluation ensures that only as many elements are required by the context will actually produced. For example, make8 of 1011 is that. Transmission. We can now define a function that encodes a string of characters as a list of bits by converting each character into a Unicode number, converting each such number into an 8-bit binary number, and concatenating each of these numbers together to produce a list of bits. Using the higher order function map and composition, functions map and composition, this conversion can be implemented as follows. Encode string to bit. To decode a list of bits produced using encode, we first define a function chop8 that chops such a list up into 8-bit binary numbers. Chop8 list of bits to list of bits. Chop8 of the empty list. Chop8 of bits is take 8 bits. Chop8 drop 8 bits. Now it is easy to define a function. I'm surprised this is not in the standard library. Couldn't you write like a function that does like that groups all the elements? Like just a function chop that takes n, that takes 8 as an argument, and then gives a list. And then takes a list and returns a list of lists where each element is a list of size n. It is now easy to define a function that decodes a list of bits as a string of characters by chopping the list up and converting each resulting binary number into a Unicode number and then a character. Decode bit to string. Decode is map bin to int chop8. Oh yeah. Oh yeah, we haven't. no. Oops. Huh? 1, 2, 3, 4, 5, 6, 7, 8. Wow, very nice code from the book. Decode. Map cur into int chop 8. Chop 8. Oh, okay. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah, it was my fault. Oh my god. Huh. Yes. Let's swap the windows back around though. Okay, finally, we define a function, transmit, that simulates the transmission of a string of characters as a list of bits using a perfect communication channel that we modeled using the identity function. Transmit string to string, transmit, decode, channel, encode. Channel. Oh, you can just use a function that you haven't, like the order in which you declare them doesn't matter. Transmit. Hello. Oh, I thought he was gonna like do something with compression now. Okay, voting algorithms. Wow. For our second extended programming example, we considered two different algorithms for deciding the winner in an election. The simple first past the post system. And the more refined alternative vote system. First past the post. In this system, each person has one vote, and the candidate with the largest number of votes is declared the winner. For example, if we define votes is a list of strings. Votes red, blue, green, blue, blue, red. The candidate green has one vote, red 2, blue has 3, and hence is the winner. Rather than making our implementation specific to candidate names represented as strings, we exploit the class system of Haskell to define our functions in a more general manner. First of all, we define a function that counts the number of times that a given value occurs in a list for any type whose values can be compared for equality. This function could be defined using recursion, but a simpler definition is possible using higher order functions by selecting all elements from the list that are equal to the target value and taking the length of the resulting list. Count, for example, count red votes is 2. Let's type that. Count red. We haven't defined votes. Oh no. Votes is red. Maybe we should just copy this. Oh. The standard indentation in Haskell mode for Emacs is very strange. Like it seems it just wants to indent everything. Votes, I don't know. Count red votes. In turn, the higher order function filter can also be used to define a function that removes duplicate values from a list. rmdupes. For example, rmdupes votes red, blue, green. The function count and rmdupes can then be combined using, well, let's first copy that. Oops. We just wrote that. Oh. Why is it? The functions count and rmdupes can then be combined using a list comprehension to define a function that returns the result of a first past the post election in increasing order of the number of votes received. Result. I feel like right now he's making heavy use of type classes, and I don't think he has explained that, right? Has he? I mean, ord is something that's ordered. Ec is something that you can use equals on. Has he explained that? I'm not sure. Oops. Variable not in sort scope. In scope sort. I mean, we can copy quicksort from somewhere. We need to import data list. Wait, no. Wow. Winner is second composed with last of a result. Okay, yeah. For example, winner votes is blue. Why does he need oh yeah, this is selecting the second element from the tuple. I thought it was like the second from the list, but that wouldn't make sense. Last picks the last one, and the second picks blue from the tuple. Alternative vote. In this voting system, each person can vote for as many or as few candidates as they wish, listing them in preference order on their ballot. First choice, second choice, and so on. To decide the winner, any empty ballots are first removed. Then the candidate with the smallest number of first choice votes is eliminated from the ballots, and the same process is repeated until only one candidate remains, who is then declared the winner. For example, if we define ballots as follows, then the first ballot has red as a first choice and green as second, while the second has blue as the only choice, and so on. Now let us consider how the winner is decided for this example. First of all, red has the smallest number of first choice votes, just one, and is therefore eliminated. Within these revised ballots, candidate blue now has the smallest number of first choice votes, just 2, and is therefore also eliminated. I wonder how much. Okay, then he's gonna do exercises. Maybe we should just skip this and go to the exercises. Yeah, let's do that. Exercises show how the list comprehension can be re-expressed using higher order functions map and filter. Okay. So that is I think let's define those. Map F over, or we can use the dollar. Filter P of X's. Okay, without looking at the definitions from the standard prelude, define the following higher order library functions on lists. A. Decide if all elements of a list satisfy a predicate. My all. Define the following higher order library functions on list. Okay. My all is a function, we'll call it predicate. And a list of bools is fold, oh no, fold, R, and bools. Nope. It goes from A2 bool to list of A's to bool. It takes a function and a list of bools. Ah, wait, we need to. How does. Yeah, I think we need to add true here. My all even 2, 4, 6 2, 4, 6 1. Yeah. Decide if any element of a list satisfies a predicate. My any. Oops. Hello. Okay. My any even 1, 2, 3. My any even 1, 3. My any even 2, 2, 2. I think that works. Select elements from a list while they satisfy a predicate. My take while A2 bool A. I don't know about that one. I think we could it's something with filter. Is it? I mean, we could zip everything with itself. I mean, zip the list with itself, and then map the predicate over the first of everything. And then, no, I don't know about this one. This is the first exercise that I can't solve. So yeah, it's been an hour.